Hi everyone! In this video, I will be discussing my findings from Lab 2, Motion of a Falling Object. The objectives for this lab are to film the motion of a falling object that is dropped from rest, and then to analyze that film to find the object's position at a specific time. Then we will create a visual representation through computer code that shows the effects of gravity alone on the object, and then we will create another visual representation through computer code that shows the effects of gravity and drag on the object. Then we will compare our real-world observations to our computer simulations, and we will use Newton's second law to observe and analyze the behavior of the object's motion. The main physics principle used in this lab is Newton's second law. I used Newton's second law to calculate the net force on our falling object. We also used the law for our position update and velocity update formulas. These formulas will be featured in the code to help orchestrate our computer models. In my tracker video, I dropped a crumpled up sheet of paper which had a final position of negative 2.871 meters. The weight of the paper was 0.0045 kilograms. This all happens over the course of 0.833 seconds. From our data, we see that the paper's movement in the y direction can be described as accelerating downwards and then falling at a constant rate. For the code, we make the following changes. We update the mass, position, and velocity of the paper and the time. We use the following formulas in our calculations: weight, drag force, and net force. For our net force considering only gravity, we simply set the net force equal to weight. For our net force considering both gravity and drag, we set our net force equal to weight plus the drag force. For our drag force calculation, we need to choose the ideal B, which represents the proportionality constant of the magnitude of the drag force. B was chosen by guessing and checking and comparing our gravity and drag data to our real-world data. When the computer-simulated data matches our real-world data pretty closely, we know that we've chosen a good B, and I ended up choosing 0.004. We also update our position and velocity formulas. For my aero scale, I chose to set it equal to 50 since our paper is very light, so we need our aero scale to be somewhat large in order to represent gravity and drag force. Aero 1 represents gravity, so we set it equal to weight times the aero scale, and aero 2 represents drag force, so we set it equal to drag force times the aero scale. On the left, we see the result of our code considering only gravity, and on the right we see the results of both gravity and drag force. Since there is no air resistance on the left, the gravity model estimates that the final position will be about negative 3.4 meters, whereas our model on the right much more closely reflects our real-world data. When we lay the data on top of one another, we see that the gravity data overpredicts our data, and that the gravity and drag model's endpoint is much closer to our actual data, so the latter is a better prediction. We are asked to evaluate the velocity graphs produced by our codes. The gravity-only graph is constant, whereas the gravity and drag graph has a slight curve. The gravity and drag graph better predicts terminal velocity because a graph that is slightly curved must eventually level off, which means that terminal velocity has been reached. We are then asked about a scenario where the object is initially thrown downward. If the ball is dropped downwards, it will reach its terminal velocity quicker, but the terminal velocity will be the same because terminal velocity is dependent on mass, surface area, and density of the medium it's falling through, and none of that is changing. From this lab, I learned that by accounting for drag, we are given data that much more closely follows our real-world data. So for problems in our physics textbook that tell us to neglect air resistance, this lab shows that although those problems are good practice, if the force of drag is big enough, then the answers we produce for those problems are not entirely accurate.